Hi guys, welcome back to my channel. Before we proceed to our new math concept for today, please don't forget to hit the subscribe button and the notification bell for more videos. So today we're going to talk about a new math lesson which is related to polynomial functions. And these are the remainder theorem and the factor theorem. So for my students, you can actually read more about it from page 94 to 104 of our reference book. Alright, but before that, before we proceed to the two theorems, it's really important to review first the process of evaluating polynomial functions. So in the previous videos, we are able to learn the two methods, wherein the first method is what we call the synthetic substitution and the other one is what we call the direct substitution. So it's up to you if what method are you going to use in evaluating polynomial functions. And when we say evaluating as a review, it's a way of substituting the value of the variable to the polynomial functions for you to be able to get the exact value of the p of c. So it is also what we call the remainder when you perform the division on polynomials. So let's proceed to the first one. Number one, we have p of x equals 3x raised to the fourth power plus x cubed minus 2x squared plus x plus 12. And then we have the divisor or the value of x. So we have x plus 1. So the first thing that we have to do here is to solve for x. Okay? But in this method, we are going to use synthetic substitution. So we can also use direct substitution, but it's up to you. But before we start, I would like you to have your calculators with you for you to easily follow this lesson or this math concept. So let's start. Before we start, of course, with the synthetic substitution, you have to make sure to solve for x. If it is not solved, x here is equal to opposite of positive 1 is negative 1. And then the next thing is you have to make sure that this dividend or the polynomial function is complete and arranged. So from the highest degree up to the lowest degree. So let's check. So from the highest degree, 4, 3, 2, 1, 0. So therefore, it is complete and the degree of the polynomial is quartic. Then the next thing is, if it is complete, we can now remove the coefficients. 3 here. Then here we have 1. We have negative 2, 1, and 12. Then the next thing is, we can now perform the synthetic substitution. Alright, so our divisor is negative 1. And then let's put an equal sign. And then the first thing is, so you bring down 3. The first coefficient must be brought down. That's the initial step. And then 3 times negative 1. Okay. So we are going to perform multiplication and addition until we reach the last coefficient. So 3 times negative 1 is negative 3. You put it here and then add. Negative 3 plus 1 is negative 2. Then multiply again to negative 1. Negative 2 times negative 1 is positive 2. And then negative 2 plus 2 is 0, of course. So they are opposite. They are opposite. Okay, so therefore it's 0. 0 times negative 1 is 0. And then 1 plus 0 is 1. Then lastly, 1 times negative 1 is negative 1. Then add 12 plus negative 1 is 11. Whatever is the last answer here when you are evaluating, this is now your answer. P of negative 1 is equal to 11. But in division, that is what we call the remainder. Okay? Next, let's have number 2. I hope that you are able to follow this one. Then number 2, we have P of x equals x cubed minus 6x squared plus 11x minus 6. And our divisor is x minus 1. So we have to solve this one. Okay, x equals positive 1. So to differentiate the two methods in evaluating polynomial functions, let's use the other one, which is the synthetic or the direct substitution. So P of 1. So when you use direct substitution, you don't care if the polynomial is complete and arranged. So just directly substitute. So P of 1 is equal to 1 cubed minus 6 times 1 square plus 11 times 1 minus 6. You can actually directly solve this on your calculators. Just make sure to write properly or enter properly the exponent for you to be able to get the right one. So when you are entering the exponent just like this, in some calculators the symbol for exponent is this, and in some calculators it's like this. Okay, so it depends on the calculator that you are holding right now. Alright, so if you are able to get 0, that is the correct answer. So P of 1 is equal to 0. So as you can see, in the first example, the value of P of x is 11 in terms of negative 1, and then P of 1 is 0. So if that's the case, those are the things that we are going to use now, evaluating polynomial functions to better understand the remainder theorem and the factor theorem. So how are we going to get 0? So what's the difference of getting non-zero remainder or zero remainder? So those are the things that we're going to have now. Now let's have the first one, the remainder theorem. Of course, since we're talking about theorem, so theorem or corollaries, these are statements that needs to be proven in mathematics before we accept them as fact. Unlike when we say postulate, or if the specific concept is postulate or statement is postulate, it means that it is universally accepted as truth. Okay? Now let's have remainder theorem. This is now the conditional statement. If a polynomial p of x is divided by x minus c, then the remainder is r is equal to p of c. So what we are proving here is that if r is equal to p of c, then the polynomial function of x is divided to x minus c. So when you divide p of x, or the dividend, to the divisor, you will be getting a remainder which is equal to p of c, or the polynomial function wherein c is substituted. Okay? So that's it. Now, when we say theorem, of course, we have to prove it. So the proof is, consider the division algorithm when the dividend p of x is divided by x minus c. We can write the division algorithm as follows. So p of x equals d of x times q of x plus r of x. So let's talk about them one by one. P of x is your dividend, equals d of x. D of x is your divisor, which is x minus c, and q of x is your quotient, plus r of x is also what we call the remainder. Alright? So to complete the proof, let us evaluate using the division algorithm. Evaluate p of x at c. So evaluate p of x at c. So it means that we are going to substitute or change all the values of x to c. Okay? So we have now p of c equals c minus c times q of c plus r. So then the next thing is, let us simplify this using some algebraic techniques. C minus c is 0 times q of c plus r. Then 0 times q of c is also 0. So therefore, what will remain is r. We are able to prove now that p of c is equal to r. And that is the remainder theorem. So if you are going to substitute the value of c to the polynomial function of x, or p of x, you will be having this statement that p of c is equal to r. That's the one that we are proving, that the remainder is equal to the polynomial function. Okay? Next, example 2. Use the remainder theorem in evaluating the following. So it's up to you if you would like to use the direct substitution or the synthetic substitution in simplifying this. So but for the meantime, let's use the synthetic synthetic substitution so that you can compare if which is much more easier to use the synthetic substitution or the direct substitution. In this case, we have p of x equals 3x cubed plus 4x squared minus 5x plus 6. So let's check this one if it is complete or arranged. So just look at the degree, 3, 2, 1, then 0. So therefore, it is a complete polynomial function, and it is arranged in descending order from the highest degree up to the lowest degree. And then the value of x, or p of c, is equal to p of negative 3. Okay, now let's proceed. Remove 3, 4, negative 5, and then 6, and your divisor is directly negative 3. Then equal sign, bring down 3, times negative 3 is negative 9. Then 4 plus negative 9 is negative 5. Then negative 5 times negative 3 is 15. Plus negative 5 is 10. 10 times negative 3 is negative 30. then add 6 plus negative 30 is negative 24. The last answer or the remainder is negative 24, so therefore P of negative 3 is negative 24. So the statement P of C is equal to R is now P of negative 3 equals negative 24 based on the given. So we're able to prove now that when you divide the polynomial function to the divisor, okay, so you are able to get the remainder, which also the value of the P of C. Alright, so this is now your answer. Next, B. P of x equals x cubed plus 5x minus 7, and then wherein we have x minus 1. So solve this first, x equals 1. But here, let's use direct substitution. So P of 1 is equal to, just change all the values of x to 1 cubed plus 5 times 1 minus 7. Again, you can use your calculator in directly simplifying this or evaluating this for you to be able to get the value of P of 1. So in this case, the answer is P of 1 is negative 1. That's it. Next, letter C. P of x is equal to x raised to the 4th minus 10x cubed plus 2x squared minus 8x plus 5. We have the value of x, which is 10. So since we have P of 10. Now let's use the synthetic substitution here. Let's check the dividend if it is complete and arranged. X raised to the 4th, 3, 2, 1, 0. And as you can see, from the highest degree up to the lowest degree, they are there. But you have to make sure that if the polynomial function is incomplete or the dividend is incomplete, please make sure to complete it before you start performing the synthetic process. So let's now remove. Our dividend is 10. The first coefficient is 1. The second is negative 10. The third is 2. The fourth is negative 8. And then we have 5 equals. So bring down 1 times 10 is 10. Then negative 10 plus 10 is 0. 0 times 10 is 0. Plus 2 is 2. Then 2 times 10 is 20. And then 20 plus negative 8 is 12. And then 12 times 10 is 120. And then you add 5 plus 120 is 125. So the last coefficient is 125, and this is also your remainder, and that's the answer that we need. We have now P of n equals 125. So using the remainder theorem, you're able to prove that P of C is equal to R. Next, how about this kind of example under remainder theorem? The expression x cubed minus kx squared plus 5x plus 3 leaves a remainder of negative 11 when divided by x minus 2. Find the value of k. So we are looking for the value of k, and this and k is one of the coefficients. And then as you can see here, we have the given remainder. We don't need to solve it, which is negative 11. And the divisor is x minus 2. So we can also make this as x equals positive 2. Alright, so let's proceed. So we are proving the remainder theorem that P of C is equal to R. So this is also R equals P of C. They are just the same then. Alright, so if that's the case, we have the given value of the remainder, which is negative 11, and the divisor, and we are looking for k. So in this case, we can just simply substitute R, which is negative 11, and then we can also use the value of x, which is 2, and then the value of k is unknown. That's the one that we are going to solve. Then the next thing is substitute the values. Your R is negative 11 equals your P of C. It doesn't necessarily mean that you are going to substitute 2 to this C. X equals 2 is also your C. Okay? Then the next thing is you will be substituting the values here. So the value of X here. Okay? So just change X to 2. So your P of C is also this one. Okay? So we have 2 cubed minus k times 2 square plus 5 times 2 plus 3. Okay? So we have this now. Then the next thing is we have to simplify this for us to get the value of k. So using some algebraic techniques. So for you to easily solve it, just make sure to solve them one by one. So you can actually directly use your calculators in solving. So you bring down negative 11, then 2 cubed is, or 2 times 2 times 2 is 8. Then 2 times 2 is 4. times negative k, of course, it's negative 4k. Then 5 times 2 is 10. Then bring down 3. Then the next thing, guys, is you have to combine the similar terms. We have 8 plus 10 plus 3. So negative 4k, and then 8 plus 10 plus 3 is equal to 21. Okay? Then the next thing is we have to isolate negative 4k. We have to isolate negative 4k by removing positive 21. Using addition property of equality, get the opposite of positive 21, which is negative 21. It's now negative 11 minus 21 equals negative 4k. Then the next thing is combine the two similar terms or constants. Negative 11 minus 21 is negative 32 equals negative 4k. Isolate k by dividing both sides by negative 4. So negative 4 divided by negative 4 is 1. And then negative 32 divided by negative 4, k is equal to 8. So that's how you solve for the value of k using the remainder theorem. You should have your remainder and of course the divisor. So you are going to use the statement that P of C is equal to R, or R is equal to P of C. To better understand and to be familiar with this one, let's have the same example as this. Example 4. The expression 2x cubed plus 3x squared plus 2x plus k leaves a remainder of 5 when divided by x plus 2. Find the value of k. So your remainder here is 5. And we have x plus 2. This is also x equals negative 2. And then we are looking for the value of k in terms of this polynomial function. So it's actually the constant term. Now, we are proving that the remainder is equal to P of C. That's the statement of the remainder theorem. Then wherein the value of the remainder is 5. And then the value of x is negative 2. Then we are looking for the value of k. That is the known value. Then the next thing is we are going to substitute the values now. Your remainder is 5. Change r to 5. And then the polynomial function, change all x to negative 2. So we have now 2 times negative 2 cubed plus 3 times negative 2 square plus 2 times negative 2 plus k. Then the next thing is we are going to simplify them one at a time. So 2 times negative 2 cubed is negative 16. And then 3 times negative 2 square is positive 12. And then 2 times negative 2 is negative 4. And then bring down k. Then the next thing is we need to combine the similar terms, bring down 5. Negative 16 plus 12 minus 4 is negative 8 plus k. Then we need to isolate k by removing negative 8 and get its opposite. So it's now 5 plus 8 equals k. Then simplify, your k will be equal to 5 plus 8, which is 13. As simple as that. So if you are already familiar with the steps in solving for the one of the coefficients or the constant itself, you can actually follow the process, and this is very simple. That's it for remainder theorem. So if you have questions and clarifications regarding the examples that we have discussed, you can comment down below, and for my students, you can message me directly. Okay? Next, the factor theorem. This is the last one. So before we go ahead and discussing the different examples under factor theorem, you have to make sure to prove it first. So theorem, factor theorem. So these are now the conditional statements that we're going to use. Let P of x be a polynomial. Then letter A, if P of C equals 0, then x minus C is a factor of P of x. And then they are just the same. If x minus C is a factor of P of x, then P of C is equal to 0. So in this case, the remainder is 0. So if the remainder is 0, it says here that x minus C is a factor of the polynomial function of x. Again, in the previous theorem, so we have a non-zero remainder. That's the one that we are using. But in this case, automatically, for you to say that the binomial or the divisor is a factor of P of x, the remainder must be 0. Now, let's have the proof. Consider the division algorithm again when the divisor is of the form x minus c. Now, example 5. Prove that x minus z is a factor of P of x, and then following the theorem, take note that the remainder should be 0. Next, example 5. Prove that x minus z is a factor of P of x. Take note that the remainder should be 0. So, I just repeat that. So, P of c is equal to c minus c times q of c plus 0, because according to the statement, take note that the remainder should be 0. And then the next thing is c minus c is 0 times q of c plus 0. So they are all 0. So therefore, p of c is 0. And then, so we can now write down that since p of c is equal to 0, therefore, 3 dots means therefore, x minus c is a factor of the polynomial p of x. So how are we going, when are we going to say that it's a factor of the polynomial function? If the remainder, or if and only if the remainder is equal to 0. Okay, but if it's not equal to 0, it's not a factor of p of x. That's it. That's just very simple. Let's have the sixth example. Determine whether x plus 1 is a factor of 2x cubed plus 5x squared plus 4x plus 1. So we need to determine if x plus 1 is a factor. How are we going to find out? We have to have a remainder of 0 for us to say that x plus 1 is a factor. So x plus 1, opposite of positive 1 is negative 1. Always do that. And then, here let's just use direct substitution. So p of negative 1 equals, change all x to negative 1, 2 times negative 1 cubed plus 5 times negative 1. You can directly use your calculators in doing this. 4 times negative 1 plus 1. Then the next thing is, what is p of negative 1? I'll be waiting for you. So p of negative 1 is 0. Okay, that's the remainder. Now, since, just write it down, p of negative 1 is 0, so since it is 0, therefore, we can say that x plus 1 is a factor of p of x. So p of x is this. Okay, p of x is this. So if it's not 0, again, it's not a factor. But in this case, it is 0. That's why we concluded that it's a factor of p of x. So let's have the same example. Determine whether x minus 4 is a factor of 2x cubed plus x squared minus 2x minus 15. So x is also 4. We are going to determine if x minus 4 is a factor. Then next is, let's use the synthetic substitution to differentiate the two. Now, let's check if this is complete, and according to what we are seeing right now, it's complete from 3 to 1, 0, and then it is also arranged. So our divisor is 4, and then just remove the coefficients, 2, 1, negative 2, negative 15. Let's see if we have a remainder of 0. 2, bring down 2 times 4 is 8, plus 1 it's 9, times 4, okay, it's 36. And then 36 plus negative 2 is 34. Then 34 times 4 is 136. And then plus negative 15, it's 121. This will serve as your answer. Now, since p of 4 is equal to 121, therefore, we can say that x minus 4 is not a factor of p of x. As simple as that. Okay, so it's not a factor because the remainder is a non-zero and it's 121. Next, let's proceed to example A. Find k such that x plus 2 is a factor of 2x cubed plus x squared minus kx minus 6. So how are you going to differentiate it from the same examples of this from the remainder theorem? You have to take note that we are talking about factor theorem, and then in factor theorem the remainder is always 0, and then we are assuming here that x plus 2 is a factor for us to be able to solve for the value of k. Now, in the previous one, we are using this statement that r is equal to p of c. But in factor theorem, we are assuming that the remainder is 0 for us to say that x plus 2 is a factor. Therefore, 0 equals p of c. And then the values that we are going to use are r equals 0. Of course, that's automatic. And then x is equal to negative 2. And then we are looking for k. So did you see now the difference between remainder and factor when solving for the coefficient? So in remainder, we have the value of the remainder as well. It's a non-zero, but here it's 0, always 0, because we are assuming that the binomial is a factor of the polynomial function. Then the next thing is, let us substitute the values, bring down 0, equals, change all x to negative 2, 2 times negative 2 cube, plus negative 2 square, minus k times negative 2 minus 6. So in that case, let's bring down 0 and then simplify them one at a time. Again, you please simplify them one at a time. So now we have 2 times negative 2 cube. Negative 2 cube is negative 8 times 2, it's negative 16. Then negative 2 times negative 2 is positive 4. Then negative k times negative 2 is positive 2k. And then bring down negative 6. Then same thing, we have to combine the coefficient or the constants. So 2k, and then we have negative 16 plus 4 minus 6. Negative 16 plus 4 is negative 12. Minus 6, it's negative 18. Then the next thing is, we need to isolate 2k by getting the opposite of negative 18, which is positive 18, equals 2k. So to isolate k, finally, we need to divide both sides by 2 to omit 2 here. And 18 divided by 2 is 9. So the final answer is 9. That's the value of k. Next, let's have the last example. Same as the previous. Find k such that x minus 3 is a factor of x raised to the fourth minus kx cubed minus 2x squared plus 3x plus 9. So the value of x that we are going to use here is x equals positive 3. Now, we have the statement 0 equals p of c. Then the value of r is automatically 0 because we are assuming that x minus 3 rather is a factor, and then x equals 3, and then we are solving for k. Then substitute the values, bring down 0, and then change all x to 3. So 3 raised to the fourth minus k times 3 cube, then minus 2 times 3 square plus 3 times 3 plus 9. So bring down 0, 3 raised to the fourth is 81, then 3 cube is 27 times negative k is negative 27k. Then the next thing is 3 square is 4 times negative 2 is 3 square is 9 times negative 2 is negative 18. Then 3 times 3 is 9, bring down 9. So what we are going to do here is to combine all the similar terms. So 0, 80 equals negative 27k. Then 81 minus 18 plus 9 is 81. And then isolate negative 27k by getting the opposite of 81, which is negative 81, equals negative 27k. Then divide both sides by negative 27. So the final answer is k equals 3. That's how you simplify. Okay, that's how you solve for k. Now, those are the two theorems about polynomial functions to take note. Alright, so please don't forget the difference between the two and the process that we need to follow in solving for the unknown terms using these two theorems. So for my students, please do this activity, and then okay, so if you have questions or clarifications regarding this, you can message me directly. You know how to do it. And then for those who are watching here, please don't forget to hit the subscribe button and the notification bell for more videos. Again, this is Teacher Dong, and have a nice day to everyone.